Hello everyone, welcome back to my channel. I hope you are all doing good. I am Tejaswini studying for SMB at Sri Venkateswara College of Engineering, Bangalore from the Department of Basic Science. Today we're gonna learn about the subject Applied Physics. Let us discuss the topic of Heisenberg's uncertainty principle and its applications. Let's begin with the topic. Introduction. Heisenberg's uncertainty principle. It is refers to one of the most significant ways of differentiating between quantum mechanics and classical physics. Heisenberg's uncertainty principle asserts that the more exactly the location is recognized, the further uncertain the momentum is, and vice versa. When the momentum is precisely known but the position is unknown, this is very different from what Newtonian physics suggests. It asserts that given sufficient technology, all particle variables may be traced to an infinite degree of uncertainty. This is a basic principle of quantum physics that explains why a scientist cannot simultaneously measure many quantum variables. Let us learn about the importance of Heisenberg's uncertainty principle in detail. The dual nature of a wave particle is the major cause of the origin of the uncertainty principle. Since each particle has a wave structure, the probability of detecting particles is greater where the waves and undulations are greatest. The wavelength becomes more ill-defined as the particle increases, which aids in determining the particle's momentum. This demonstrates that particles with specified positions do not have a constant or set velocity. The precise velocity is given by a particle with a well-defined wavelength. As a result, precise measurement of one quantity causes significant uncertainty in the measurement of the other. What is Heisenberg uncertainty principle given by the expression? Heisenberg uncertainty principle, it states that the position and momentum of microscopic moving particle cannot be determined simultaneously with accuracy or certainty. The mathematical expression is given by delta x into delta p greater than or equal to h by 4 pi, where delta x is uncertainty in position, delta p is uncertainty in momentum, where h is Planck's constant. Applications of Heisenberg's uncertainty principle. The application of Heisenberg's uncertainty principle are as follows. In the nucleus, there are no free electrons, demonstrating that an electron cannot exist within a nucleus, estimating the ground state energy of a system, proving the existence of proton and neutron inside a nucleus, the width of spectral lines. Here are some key points of the Heisenberg's uncertainty principle. It is also known as an Heisenberg's indeterminacy principle. It states that the more accurately one property is measured, the less accurately the other property can be known. It's commonly applied to the position and momentum of a particle. It states that the more preciously the position is known, the more uncertain the momentum is, and vice versa. It states that we cannot measure the position and the momentum of a particle with absolute precision. It's mathematically given as delta x into delta p greater than or equal to h by 4 pi, or delta x into delta mvx is greater than or equal to h by 4 pi, or delta x into delta v into x is greater than or equal to h by 4 pi m. What are the limitations of Heisenberg's uncertainty principle? According to Heisenberg's uncertainty principle, it is impossible to calculate the position and the momentum of a small moving object like electron simultaneously and accurately. The principle only applies to microscopic particles and not to macroscopic particles. Conclusion: Heisenberg's uncertainty principle has a significant impact on how experiments are executed in science. Considered determining a particle's momentum or position. To make a measurement, you need to interact with the particle and change its other variables. A collision between an electron and another particle, such as a photon, is required to monitor the position of an electron. For example, this will transfer some of the momenta of the second particle to the electron being measured, causing it to change. A particle with a shorter wavelength and hence more energy would be required for a more accurate determination of the electron's position, but this would shift the momentum more during contact. That's all for this video. Thank you. Have a nice day.